Dentine desensitizers. These preparations decrease hypersensitivity of teeth when applied to their outer surface, especially where erosion has occurred near the gum line. Ammonical silver nitrate solution. Formaldehyde solution, liquefied phenol, zinc chloride and strontium chloride are used as desensitizer in toothpaste form. Alveolar analgesics. These are liquids or pastes used by dental surgeons for the symptomatic relief of pain arising from post-extraction alveolitis, dry socket, for example, benzocaine, clovol. Pharmaceutical aids. They are needed for many purposes like preservation, stabilization, suspending, excipient, adsorption, filtration, prevention of oxidation, solubilization, complexation like tale, kaolin, bentonite, etc. Radiopharmaceuticals. The substances which emit radiation and which are used in medicine are called radiopharmaceuticals. The term radioisotopes, radioactive isotopes, radionuclide and isotopes are used generally for substances which emit ionizing radiations. These are used in medicine for the following two purposes. I. As source of radiation for radiotherapy, for example in cases of cancer. 2. As radioactive tracers for diagnostic purposes. Structure of atom, a brief revision. Atoms contain many subatomic particles. However, for this chapter the following three subatomic particles are important. 1. Protons. These are positively charged heavy particles, found in the nucleus of an atom. Each proton possesses a unit positive charge. 2. Electrons. These are negatively charged light particles, orbiting around the nucleus. Each electron possesses a unit negative charge. The charge of an electron is equal, but opposite, to the charge of a proton. 3. Neutrons. These are heavy particles found in the nucleus. These do not possess any charge. The mass of a neutron is almost equal to the mass of a proton. Atomic number. 1. Atomic number of an element is equal to number of protons present in the nucleus of its atom. 2. As the atom as a whole is neutral, therefore the number of electrons outside the nucleus must be equal to the number of protons inside the nucleus. Atomic number of an element is the serial number of its position in the periodic table and determines its chemical properties. Mass number. It is the sum of the number of protons and the number of neutrons in the nucleus. Mass of an atom of an element is due to the mass contributed by protons and neutrons present in its nucleus. Mass of an electron is negligible. Mass number equals number of protons plus number of neutrons. Both the atomic number and mass number of atoms can be represented by writing them in the following manner. 4/2He12/6C31/15P35/17Cl39/19K. It shall be seen that the superior figure, i.e., the numbers at the top and to the left of the symbol represent the mass number of the atoms. The inferior figure, i.e., the numbers at the bottom and to the left of the symbols represent the atomic numbers of the atoms. The right side of the symbol is kept free for representation of number of atoms, state of ionization, etc. For example, Cl means a molecule of chlorine each of whose atoms has a mass number of 35 and atomic number of 17. As the atomic number of an element always remains the same, therefore, the subscript can be omitted. As examples for He, 12C, 31P, 35C1, 39K, etc. It is also a common practice to write out the full name of element followed by the mass number, for example, helium 4, chlorine 35, etc. Sometimes only the symbol is written followed by the mass number such as E4, C12, P31, C135 etc. Isotopes. Atoms of an element which have the same atomic number but which have different mass numbers are called isotopes. In other words, isotopes are atoms of the same element whose nuclei contain the same number of protons but different number of neutrons. Isotopes of any element contain the same number of protons and the same number of electrons and, therefore, these exhibit the same chemical properties and occupy the same position in the periodic table. Isotopes are classified into the following two types. 1. Stable isotopes. These are stable and do not emit radiations such as carbon-12, chlorine-35, hydrogen-1, protium, hydrogen-2, deuterium etc. 2. Radioactive isotopes. These are unstable and emit radiations. These may be naturally occurring radioactive isotopes, uranium, radium etc., or may be produced artificially. The phenomenon of emitting radiations by these isotopes is known as radioactivity, and such isotopes are called radioactive isotopes. Types of radionuclides. Radioisotopes are of two kinds, namely, I. Natural radionuclides, and 2. Artificial radionuclides, produced in nuclear reactors in controlled manner by reactor irradiation or cyclotron irradiation. There are about 40 natural radionuclides, e.g. U-235, Ra-226, Ab-87, K-40, etc. Nature of radiation. 3 different kinds of radiations with different types of behavior are observed from radioactive substances. These are named as alpha particles, A particles, beta particles, B particles, and gamma rays, Y rays. In a radioactive change, a nucleus usually loses just one particle, alpha or beta, and it is frequently accompanied by a gamma ray. During this process of radiation, the unstable nucleus of a radioactive isotope gives out energy and gets converted into a more stable form. 1. Alpha particles, C particles. These particles are composed of 2 protons and 2 neutrons and are identical to the nucleus of a helium atom. Hence atomic number of alpha particle is 2 and its mass number is 4. These are heavy but slow and are least penetrating. These can be stopped by a piece of thin paper. These penetrate into the tissues for only 0.01 cm. 2. Beta particles, B particles. These particles are simply electrons emitted by nucleus. These have unit negative charge. These have negligible mass but their energy and velocity are very high. These particles can penetrate into the tissues to the extent of 1 cm or slightly more. In other words, penetration of B particles into the tissues is about 100 times more as compared to penetration by alpha particles. 3. Gamma rays, Y rays. Gamma ray is a radiation of entirely different character. It is a form of electromagnetic radiation like visible light. It travels with the same velocity as the visible light. Gamma rays, like X-rays, have a much shorter wavelength as compared to visible light. Gamma ray have much more energy and much greater penetrating power. These can penetrate in the tissue to about 100 centimeters. In other words, penetration power of gamma rays is about 10,000 times more than the alpha particles and 100 times more than the beta particles. These do not have any positive or negative charge. Unit of measurements of radioactivity. Unit of radioactivity is Curie. Its symbol is C or C. It is defined as the quantity of the radioactive substance undergoing 3.7 by 1010 disintegrations per second. This is equal to about Igm of radium, which also undergoes 3.7 by 1010 disintegration per second. It is a large unit, and in actual practice the following subunits of Curie are used. A. Millicurie, i.e., mc. This is 1 by 103 of Curie. It undergoes 3.7 by 107 disintegrations per second. B. Microcurie, i.e., U. This is 1 by 10 to 6 of Curie. It undergoes 3.7 by 104 disintegrations per second.